Good. Thank you, Professor Ito, for the introduction and for the opportunity to visit here and to speak today. So I'm going to be talking about research that we have done in collaboration with others and involving a great team of graduate students and other researchers both at Stanford and at other institutions. So I should begin by acknowledging the people who actually are most responsible for this work. Irene Goldthorpe was previously a student in my group. She's now assistant professor at the University of Waterloo in electrical engineering. Xu Hu also just recently graduated from my group, and he's now a postdoc at Caltech. And of course, Yoko Kawamura here at Keio University was a visiting researcher, visiting scholar at Stanford for 1 year. I'll show a few results from her work that are relevant to this topic. Also, Anne Marshall is a research scientist in the Jabal Laboratory for Advanced Materials. Kevin Wong is a graduate student in Professor Mark Brongersma's group. Nevron Ozgoven is a former student in my group, and of course Professor Ito is Yoko's advisor here at Keio and was involved in some of the discussions of this work we were doing at Stanford. I'd like to also acknowledge funding from a variety of different institutions. So the outline for today, I'd like to give a very, very brief introduction to why we're interested in Coreshell, that is coaxial heterostructure nanowires. And in particular, we're interested in such wires where we have group 4 semiconductor components in the coaxial structure, silicon and germanium. And then very quickly, I'd like to start talking about some of the results that we've obtained in studying these kinds of structures. First of all, how we grow coherent, highly strained germanium core silicon or silicon germanium shell wires, how defects are introduced into these structures if they're not grown properly, and how we have to control this. Then I'll talk a little bit about the processes by which misfit strains in these as-grown structures relax during annealing, because we're interested in ultimately using these kinds of structures in devices where annealing is important for dopant activation and things of that sort. We want to understand how we can keep the structures coherent during these annealing treatments. And then finally, I'll show a few results from Yoko's work at Stanford looking at photoluminescence as a tool to study the formation of defects and the extent of passivation of surface defects of such structures. So, just as way of a motivation in terms of interesting technology for this work, there's basically two communities of researchers who are interested in these kinds of structures right now. Those who are interested in nanophotonics and building tiny detectors and photonic elements that can be integrated on semiconductor chips. So my colleague Mark Brongersma and his group at Stanford are among these researchers. And what they're interested in is the fact that the band gap, both the indirect and the direct band gap of germanium nanowires, are consistent or similar to the typical wavelengths of light used in telecommunications. So there's an interest in germanium as a telecom material that is silicon compatible. In addition, there are other aspects of these wires that are very interesting. Germanium has relatively high electron and hole mobilities compared to silicon, and this makes it an interesting semiconductor material for certain applications. Also, when we grow a wire when we grow a semiconductor in a very thin wire geometry, we have mechanical compliance that exists because of the small radial dimension of these wires, and so we can accommodate elastic strains that are quite large. And this makes these things interesting for making strain devices. And then the high surface area to volume ratio, this can be either an advantage or a disadvantage depending on how we want to look at it. It can be a disadvantage because we're very concerned with the presence of surface defects and traps and their influence over the device. It can be a real advantage if we want to use these things as sensors, because the detection of charge by adsorption of species onto the surface will be greatly amplified compared to a planar surface because of the high surface area. So I'm showing just a few results from recent literature where people have been looking at making optical, nanoscale optical elements, photodetectors out of nanowires. Professor Brongersma's group has done some very nice work showing that even though these are nanoscale semiconductors, there are certain optical modes that can be guided along them. These are basically what are called leaky mode resonances that can form for nanowires of characteristic geometries and refractive index, and we can actually guide light in these structures, even though their size, lateral size scale is very small. There's also been a lot of interest in these kinds of devices in nanoelectronics, and in this case, the reason for the interest in these Coreshell structures is largely related to the electrostatics of a field effect device. Having the ability to surround a cylindrical channel with metal to control the gated region is a real advantage. Also, the fact that we can grow wires where we don't have to pattern the width of the channel in the typical way that's done in semiconductors. We're more flexible in the ability to achieve very small dimensions with nanowire growth. This is an advantage as well. So there's been a number of groups who've been studying these nanowire channel devices for the last 10 years. Recently, a lot of interest in these kinds of coaxial structures, similar to the ones that I'll be talking about here today. So the way that we make wires is by locally catalyzed chemical vapor deposition using a technique that's been known of since the early 1960s called vapor liquid solid growth. And in our case, we're using a solid catalyst of gold that we pass a germanium-containing vapor over. And if we look at the gold-germanium binary phase diagram, we can see that this is a system that exhibits a low eutectic melting point. So that's an interesting system for VLS growth. We want to grow these wires by the formation of a liquid droplet at low temperatures, and we can do that in this system because of the low eutectic melting point. So basically, in this kind of system, we saturate gold with germanium up to the point where we can melt the gold germanium solid and make a liquid. According to the phase diagram, we should be in the liquid phase field when say at 400 centigrade, and we get to around 28 atomic percent germanium. So we can at low temperatures make this droplet. The gold germanium droplets' surface properties and surface tension are very important. We want to have this as a well-defined liquid droplet that doesn't spread out on the surface. So it turns out that gold has a high surface energy, so gold germanium liquids tend to have high surface energies too, and this causes them to beat up on surfaces, so we can form a well-defined droplet. And this is just shown schematically here. We supersaturate this liquid droplet with germanium, and we nucleate a single crystal pillar of germanium that keeps growing with the gold germanium seed at the tip. And this can grow for many, many microns. If we intentionally pattern the gold catalyst, we can cause the wires to grow where we want to on a surface. And, or we can purchase colloidal gold that has been pre-sized by a chemical vendor, and therefore we can define the size of the lateral dimensions of the wire very well, and we can deposit those catalysts on a surface. When we do this process and we finish growth, we find that we have a gold particle at the tip of the wires. The wires always have the catalyst at the very tip as they grow, and we have an atomically abrupt interface between the germanium and the gold. And this is a 1-1-1 oriented germanium nanowire. This is the typical growth orientation that's seen for a very wide range of wire diameters. But as we get to much smaller diameter wires, smaller than 20 nanometers or so, we start to see other growth orientations become thermodynamically favored. And so I'll talk a little bit about that in a few moments. So how do we take these germanium nanowires and then make them into Coreshell nanowires? We want to make coaxial heterostructures of silicon and germanium. So what we do is, as I'll show in a moment, we do a two-step growth, the growth of the germanium core followed by the silicon shell. We're interested in these kinds of structures because the germanium core has this higher mobility semiconductor. Germanium has higher mobilities than silicon. The silicon shell can form a high quality SiO2 surface coating. We can intentionally oxidize the silicon to make an SiO2 surface, and there's a great deal of understanding of how to passivate defects at SiO2 silicon interfaces. So we can make a good quality surface passivation with a silicon shell. The difference in lattice parameters between silicon and germanium is about 4%, and by creating a coherent core shell structure then, we can create a significant state of strain in the germanium core. The germanium core is placed under very high compressive strains, and this allows us to use strain to engineer the electronic behavior of the semiconductor, as is currently done in state-of-the-art MOS devices in silicon. So we can do the same kind of strain control with these kinds of structures. And in addition, the band offsets for holes in particular, the valence band offset between germanium and silicon is very significant. So we can confine holes away from the surface of the wire if we're concerned about surface defects and scattering. So there's a lot of advantages to this structure. We grow our nanowires in a CVD system. I mentioned that it's a CVD reactor. This is a converted cold wall silicon germanium epi reactor. So some of you will be familiar with the work that was done by Judy Hoyt and Jim Gibbons over 20 years ago now on silicon germanium epitaxy at Stanford, some of the very early work in this field. This is actually that reactor that Judy Hoyt built before she became a professor at MIT. And we took it and converted it into a nanowire growth reactor. So this is a rapid thermal CVD system. It has a bank of quartz halogen lamps that allow us to rapidly change the temperature of a silicon wafer susceptor. The actual samples that we grow on sit on this silicon wafer susceptor. So we can rapidly heat up and cool down, and that turns out to be very valuable for controlling the nanowire growth process and the Coreshell formation in particular. We have a number of different gas flow channels into the reactor, so we can flow silane or germane for silicon and germanium, diborane and phosphine for boron and phosphorus doping, and hydrogen is the carrier gas. We also have HCl that's been added here, which is actually something that we use a lot in making core shell wires, and I'll show you why in a moment or two. The sample is compatible with up to 6-inch wafers. So if we wanted to make a real, large wafer experiment so that we could run wafers in the clean room, we could do that. Although, to be honest, we never do that, but we could if we wanted to. So this is the schematic of the kind of process we use to make the core shell wires. We basically grow our germanium oriented germanium nanowires and then coat them with deposition in silane by a conformal deposition of silicon or silicon germanium. We can mix silane and germane together and grow a silicon germanium alloy. And the typical kind of thermal process that we use is shown here. We heat up to a temperature slightly above the eutectic of germanium and gold, and this causes the melting of the gold to make a droplet, and the nucleation of the germanium underneath that droplet as it becomes supersaturated. This takes place for a period of just 1 to 2 minutes. And then we rapidly cool down to about 300 centigrade. And most of the nanowire growth, the germanium wire growth, is done at this lower temperature. So we actually grow the wires by VLS at a deep subeutectic temperature. But we have confirmed that it is indeed growing from a liquid droplet. So the liquid droplet is metastable under the conditions in which we grow the nanowires. The reason that this is possible is that we've actually supersaturated the droplet with germanium, and it's much more difficult for the gold to crystallize when it's supersaturated in that fashion. So we do a deep subeutectic growth. And the reason for doing that is because at these lower temperatures, 300 degrees and lower, all of the germanium is incorporated into the wire through the catalyst. There's no sidewall deposition. So the rate of sidewall deposition is greatly suppressed at lower temperatures. And that means that we grow wires that do not have inclined surfaces. They're not tapered. They're very parallel sidewall facets, so very straight and uniform in diameter. And then after the wires have been grown, the germanium wires have been grown, we can heat up without breaking vacuum. The gold is still present on the tip. The gold germanium liquid is still present on the tip, so we get some lengthening of the wires during this process, but we start flowing silane or silane germane gas mixtures, and we grow a shell on the outside. Alternatively, we could stop deposition, etch off the gold droplet, and then do sidewall deposition separately, but that has various complexities and problems, so it's cleaner for us to do this without breaking vacuum. So when we make these structures, one of the things that we're interested in is the ability to control the misfit strain between the silicon and the germanium. And in this kind of epitaxy, Coreshell epitaxy, we can think of the core as being the substrate, but it's a compliant substrate because it has a very small cross-section. So it's elastically much more compliant than a bulk wafer that we would grow on. So as we grow the shell, the lattice spacing of the core changes to maintain coherency. So a lot of the strain in the structure actually gets stored in the core of the Coreshell wire. We can solve this problem, the mechanics of this problem, and solve the elastic strains that would arise if we don't form any dislocations. And basically what we do here is we have to obey certain boundary conditions in this elasticity problem. We have to have traction-free surfaces and a continuity of the elastic stress at the Coreshell interface. So subject to these boundary conditions, if we solve for the stresses and strains, we can find that, say, for a 20 nanometer diameter germanium core and a 10 nanometer thick coherent shell of silicon, that we should have strains in the core in the radial and circumferential directions of about minus 1.35%, so that's 1.35% compressive strain, and an axial strain that's bigger than that, 2.9%. So these are very large strain values. So the question is, can we actually realize this in practice, or do the wires form dislocations or other defects to relieve the large misfit stresses that are involved? Well, the conditions under which thermodynamically these kinds of structures can be stable have been calculated by several different groups in the past few years. I'm showing some work here from colleagues of ours at Stanford. This really is work done by Bill Nix, although there are a number of other authors on the paper. This particular part of it was Bill Nix, a professor in my department, who's one of the experts in this kind of problem. And what he's doing here is assuming the formation of a perfect misfit dislocation, an edge dislocation, a loop at the silicon germanium interface in this Coreshell structure, and calculating from the energy required to form this and the reduction in the elastic energy that occurs as it forms, the maximum amount of strain that such a structure can have before it forms such defects. So if we look at a planar bulk substrate of germanium and grow a silicon film on it, we'll see a relationship sort of like this, where as the film thickness is very thin, we can accommodate large amounts of strain. We're storing that strain in the film, and as it gets thicker, it becomes harder and harder to maintain that strain level. We have a very large elastic energy storing in the film, and therefore we form dislocations at very low misfit strain levels for thick films. Now, if we're talking about a shell around a core of a germanium nanowire instead, we have a similar relationship for relatively large diameter cores, but as the core gets smaller and smaller in diameter, it becomes more and more elastically compliant, and we can support higher amounts of misfit strain before we form a dislocation. And the interesting thing that happens is the core gets very small in diameter. It becomes so compliant that we can, in principle, get up to 4% strain. The full misfit strain can be accommodated in this Coreshell structure, but we have to get to relatively large shell thicknesses to do that thermodynamically. So we have to pass through a range of shell thicknesses where, in fact, the structure is not stable. So this basically tells us that getting all the way from a pure germanium core to a pure silicon shell is very difficult. On thermodynamic grounds, we ought to form dislocations. But as many of you will be aware from research in misfitting semiconductor systems, this is just the thermodynamic picture, and actually the kinetics of formation of these defects can be very difficult. So there may be room for actually making such structures metastably, and that's what we found. So when these things actually do form dislocations, they do so in a very characteristic way. So the first thing that happens in these highly strained systems is there's roughening. So this is strain-driven roughening of the shell as it's growing during the deposition of the shell around the germanium core. And a characteristic kind of structure is seen. This shows the undulating surface roughness on the shell growing on a core of fixed diameter. So this is a small diameter core. I think it was 15 nanometer diameter germanium core, and we're growing a silicon shell on it, and you can see that we formed this sort of undulating and periodic roughness. And there don't appear to be a large number of defects in this wire at this point. If we continue to grow the shell thicker, we see that the undulating roughness, its periodicity and its amplitude are the same. They don't change. But now we start to see additional contrast in the image that's consistent with it's a Moiré contrast, consistent with a difference between the lattice parameters of the shell and the lattice parameters of the core. So we can see that some relaxation is taking place. If we continue to grow the shell thicker than that, now we can definitely see dislocations that are forming in the shell. We see these lines of very abrupt contrast, which are dislocation loops that have grown into the shell, and we can see very strong Moiré contrast. But you'll notice that the periodicity and amplitude of the roughness is not very different. So what appears to happen here is in the early stages of growth, when the shell is too thin to form dislocations, it roughens. That's the principal method for relieving the strain. Once the shell gets sufficiently thick, there's now enough elastic energy stored in it that even though it's roughened somewhat, we can nucleate a dislocation. And we nucleate many dislocations. And most of the strain is relaxed by the dislocations that form. If we grow on a thicker core to begin with, this is about a 20 or 30 nanometer diameter core, these experiments here, we can see that even for the very thin shells, we see Moiré contrast almost immediately. So they relax by dislocation formation very early on. So this roughening is driven by the misfit strain that exists in this structure. We have atomic flux out of regions of concave curvature to regions of convex curvature, building up roughness on the surface. And this roughness precedes the formation of dislocations. When we looked at this more carefully, we found that actually not only does the roughness precede the formation of the dislocations, it seems to enhance the likelihood of dislocation formation, because we have this kind of hill and valley structure where in the valleys there's very large stress concentrations that build up. So it's easy to form a dislocation in the valley of one of these hill and valley structures. And this has been observed in two-dimensional thin film epitaxy previously in this kind of system. We find in regions of local concave curvature of the surface that extrinsic stacking faults are formed in the shell. These are basically additional planes of atoms that grow into the shell by a process called climb. They appear to nucleate at the surface of the shell and grow in until they reach the interface. And they're one of the primary dislocation defects that accommodate the misfit strains in these structures. So it appears that the silicon shell roughens first, and that there's a preference for forming dislocations at the concave regions of curvature in the rough surface once the roughness has taken place. So what we thought from these experiments was that the way to make coherent structures that don't form dislocations is to avoid roughening in the first place. If we could do something to prevent strain-driven roughening of the shell, then we wouldn't have these preferred sites for nucleation of the dislocations. So we put a lot of effort into methods to avoid strain-driven roughening of the silicon shells. So the first thing that we thought was, well, if we don't grow pure silicon shell, but grow a silicon germanium alloy shell, there's going to be less strain in the system, so less driving force for dislocations anyway. So let's try that. So that was the first thing we tried. But it turned out that even for relatively small amounts of silicon in the shell, this is 25% instead of 100%, once we got up beyond a certain thickness of shell, we would always see highly defective, dislocated structures. So these are moire fringes because of the difference in lattice spacings. We have relaxed them through the formation of defects in these structures. And we can see the surfaces are not particularly smooth. They've roughened as well. However, what we found is if we introduced HCl in the growth of the shell, we could inhibit this relaxation almost completely. And what we believe the HCl does is either etch the asperities on the shell as they form during surface diffusion of the shell driven by stress, or perhaps we deposit chlorine on the surface during the shell deposition, and this chlorine that is present, it's constantly adsorbing on the surface and coming off the surface, somehow inhibits silicon surface diffusion. But in any case, the HCl flow seems to strongly inhibit the roughening of the surface, and as a result, we can make coherent, very perfect silicon germanium Coreshell structures. So these are quite large diameter wires. They can be the total diameter can be up to 100 nanometers with thick shells of silicon germanium. So this works very, very well. But of course, we'd like to be able to get all the way to pure silicon shells and not have this sort of dilute silicon germanium alloy as the shell material. Just a little bit more detail on this. If we look at the structure that we formed here, this is a 48 nanometer germanium core, this particular one, with a 12 nanometer silicon germanium shell, and it has about 1% lattice mismatch for this composition. According to those calculations from Professor Nix, thermodynamically this structure should have relaxed. It shouldn't be able to support 1% strain. The maximum strain this structure should support is about half of that value, but in fact it didn't relax. And this tells us that we have achieved a metastable state of strain in the system. It ought to relax on thermodynamic grounds, but we've inhibited that relaxation by preventing this surface roughening, which allows easy dislocation nucleation. We've also quantified the strain in these structures by using synchrotron X-ray diffraction. This is a very powerful technique for nanowires where we have relatively small volumes of material. We can quantify the axial strain component in these structures by looking at the despacing of the germanium 111 planes. These are 111 epitaxial wires growing on a 111 silicon substrate. So we can see for the bare germanium nanowire, 0 nanometers thickness of shell, we have no measured strain compared to the germanium bulk reference. If we look at a 6 nanometer silicon germanium shell, the predicted strain for this structure in the core from Professor Nix's calculations is about 0.31% compressive strain. We measure 0.22%. And for a 12 nanometer shell, the predicted value is 0.56%, and we measure 0.43%. So these values are somewhat smaller than the predicted strain values. And this suggests that something else is relieving strain. And we believe this is actually interdiffusion of the silicon and germanium under the conditions in which we grow the shell at temperatures above 650 centigrade. And I'll talk a little bit more about this interdiffusion here in a few moments. When we look at the structure of these relaxed samples where we've had a lot of roughening, we find that there's a characteristic hill and valley structure that emerges. We get facet planes for the silicon along the 111, inclined 111 planes of the 111 oriented nanowire. And these are known to be low surface energy planes for silicon and germanium. So it's not surprising that this structure should facet in this way when we form large amplitude roughness like this. But what it suggested to us is if we could create a nanowire where we had these low energy 111 surface planes along the sides of the nanowire to begin with, it might not roughen, because we would start off with surface facets that are already very low energy planes. So it turns out that when we decrease the wire diameter below about 20 nanometers, the germanium nanowires no longer grow in the 111 direction, like they do here. They actually grow in the 110 direction. And this had been previously reported for silicon nanowires by Volker Schmidt and Ulrich Güssele and co-workers. And then we observed it several years later for germanium nanowires. When we have a 110 oriented wire, it has low energy 111 sidewall facet planes. So our thought was that this structure might be more resistant to roughening because of the low energy sidewalls. And in fact, that's what we observed. So we could grow pure silicon on these small diameter wires and go all the way from a silicon crystal to germanium core, and without any evidence of dislocation, formation, or roughening. And there's two reasons why this is happening. We have the low energy sidewall facets, and we also are starting out with a smaller diameter core, which is more elastically compliant. So it's going to be able to store more strain elastically than the larger diameter 111 oriented wires would in any case. However, if we try to grow the shell too thick, beyond about, say, 2 nanometers for this 14 nanometer diameter germanium wire, 110 oriented wire, we find there is defect formation, and the defects form both twins and dislocations in these larger diameter, larger thickness shells. So there's a trade-off between the shell thickness and the germanium wire thickness that we have to understand to be able to engineer structures of a particular strain state. Another thing that we found we could do is make graded or multi-layer Coreshell geometry. So if we wanted to grow a large diameter wire with a germanium core and have silicon, pure silicon on the outside, one way to do this is to make a graded set of layers. So we have a silicon germanium shell followed by pure silicon. And this structure, we can metastably achieve very large strains in the germanium shell as a result of forming this kind of multi-layer structure. And it remains coherent across the whole wire. So we've seen that we can actually make these highly strained coherent structures mainly by inhibiting surface roughening during growth, but also by appropriate choice of wire orientation and sidewall surface facet plane. So the next thing we were interested in is how stable are they after they've been synthesized? Can we actually take these structures and anneal them and take them to temperatures at which we might do device fabrication? So in these experiments, we've started out with a silicon germanium shell and a germanium core. This particular example, we show 32 nanometer diameter germanium wires with a 2 nanometer shell. And we can estimate the composition of this 2 nanometer shell. It's about 50-50 silicon germanium. And we do that by energy dispersive spectroscopy in a TEM. So we do a line scan, an EDS line scan across the Coreshell structure, and then by collecting the silicon counts and the germanium counts and fitting them to a model for the hexagonal cross-section of the wire, we're able to estimate the silicon germanium alloy composition for the shell. We grow these in a fairly dense array, and then we can do further studies on them. I'll give you a little bit more detail on how this EDS measurement works. Basically, we know that the wires form in the 111 orientation with 6 sidewall facets. These are 112 oriented sidewall facets, and we've studied this previously for these wires. We place the wires down on a TEM grid, and they tend to sit with one of these sidewall facets on the grid surface, and then we tilt into an orientation where we're looking along the 110 zone axis, and then do the EDS line scan measurement on this kind of structure. We can compare then the measured counts to a model for a particular composition and get the best fit result for the composition. We can see that there's a higher composition at the periphery here because we're sampling predominantly composition from the shell and not from the core. When we get into this portion of the line scan, we're sampling both. So we see silicon and germanium, but the silicon content is somewhat depressed relative to the peak values at the periphery. So we wanted to look at how stable these structures are during annealing, and one interesting method to do this is in situ TEM. So this is TEM in a hot stage, and these are frames from a movie of the annealing process. And 700 degrees is the annealing temperature, and this is sort of the upper range of temperature that we would use to grow the Coreshell wire structure. So this would be a pretty high temperature for growing the silicon shell. We know from our previous experiments that at these temperatures, surface roughening can be significant and dislocations can form. So when we did this experiment, we were expecting to see roughening and formation of dislocations, but that's not what we found. In fact, we can see that the before and after images are not much different. There may be some transient roughening taking place in the middle of the time frame shown here, but it's very modest. And we can see the comparison here before and after. There isn't an obvious morphological difference for the wires in this experiment. So, however, we know that this kind of experiment is capable of relaxing the misfit strains in these structures. So one of the things that we were interested in is whether this could we could, instead of seeing roughening and dislocation formation in these in situ TEM experiments, we may be seeing interdiffusion. So if we are seeing interdiffusion, this is interdiffusion in a structure that has a very high germanium content. It's a pure germanium core with a very thin silicon germanium shell. So we looked at some of our previous work in my group and other groups looking at interdiffusion kinetics in strained epitaxial structures at this high composition range, high germanium content range. So this is some work that was done by Nevron Ozgevan in my group several years ago. She was growing approximately strain-balanced superlattices of silicon germanium with high germanium content on a relaxed silicon germanium buffer layer on silicon, and then using X-ray diffraction to characterize the abruptness of the interfaces in this superlattice structure. After annealing these structures, the superlattice peaks that you see here, this is the silicon substrate peak, this is the silicon germanium buffer layer, this is the main silicon germanium superlattice peak is Bragg peak is right next to the buffer layer peak, and then we have all of these satellite peaks that are related to the composition modulation in the structure. If we watch the rate at which these satellites decay, we can relate that to the interdiffusivity of silicon and germanium in these high germanium content superlattices. So the decay rate of the first order satellite peak here is approximately proportional to the interdiffusivity. And so we can measure that decay rate for various temperatures from 600 to 700 degrees. And we can see at 700 degrees it decays very quickly with annealing time. So after just a few minutes of annealing, we see orders of magnitude decay in this peak intensity. And from that we can estimate an interdiffusivity of silicon and germanium at 700 degrees for about a 90% germanium content strain superlattice of 1 × 10 to the minus 16 centimeters squared per second. If we take that number and we plug it into an estimation of the characteristic diffusion length at that temperature for the time frame of our in situ TEM measurements, we would predict a characteristic diffusion length of 2 or 3 nanometers. And that's basically the thickness of the silicon germanium shell. So we would expect that the silicon germanium shell is substantially washed out or diffused out after this very short heating experiment in the TEM. So we believe that the strain relaxation in this kind of experiment in situ TEM occurs predominantly through interdiffusion, and that's why we don't see this significant amount of roughening. Now the reason why the roughening seems to be inhibited and the interdiffusion plays the most important role, first of all, we're holding this at 700 degrees for 8 minutes or so, which is a lot longer than we do in our growth run. So when we grow the wires, the shells around the wires, we're only at these high temperatures for 1 or 2 minutes instead of 8 to 10 minutes. So there's less likelihood of interdiffusion during the growth than there is during the annealing. But also, we've taken these wires out of the growth environment, we've transferred them through air and put them in a TEM. So we know that there's some surface oxidation, there's some surface contamination on the wires. And in the act of actually doing the TEM, we deposit some further contamination on the wires. And this probably inhibits the roughening process in the TEM. So after the interdiffusion, or after the 8 minutes at 700 C, we can see that the peaks that we had in the composition for the shell have been completely removed, and we have effectively interdiffused the silicon and germanium in the structure. So just summarizing the various relaxation mechanisms that we see in these Coreshell nanowires, we have silicon germanium interdiffusion is one important relaxation mechanism. It seems to be most important at higher temperatures and where we have some kind of surface contamination that prevents surface diffusion and roughening. If the surface is clean, we can have, and when we're not flowing HCl to etch away asperities as they form, we can have surface roughening driven by strain in the misfitting structure. That can relieve some of the misfit strain. And what it also does is it produces these asperities and regions of high curvature, high concave curvature, at which dislocations can preferentially nucleate. And this is a schematic of such a structure where we have a grown-in edge dislocation that has climbed in from the surface and is relieving axial strain in the structure. So these appear to be the major mechanisms of strain relaxation, and which one operates depends a lot on how you treat the surface of the nanowire as you're growing it or annealing it. So the last thing I want to say in just the last couple of minutes is this is some really nice work that Yoko did while she was at Stanford in collaboration with my student Shu Hu and with student Kevin Wong in Professor Brongersma's group. And here we're trying to understand how these high surface area nanowire arrays form defects that can be observed in photoluminescence experiments, and how we can perhaps passivate these defects by forming Coreshell structures. So in this work, we're interested in looking at the photoluminescence spectrum from Coreshell nanowires. Photoluminescence is a very powerful tool for looking at defects, because defects basically can provide a means for non-radiative recombination of electrons and holes. So if we put electrons and holes into a semiconductor by shining a light on it, if we lose that electron hole population, we quench the photoluminescence that would normally be present, and we can see that then as the presence of defects. So in these experiments, Yoko started out by looking at a bulk germanium standard. So with bulk germanium single crystal, we see a strong indirect photoluminescence. This is an indirect gap semiconductor, but there's also a direct gap that is not that much higher in energy than the indirect gap. It's about 0.8 eV, whereas the indirect gap is about 0.67 eV. So we see both contributions in the photoluminescence. So this is recombination across the direct gap, the gamma point, and recombination across from the L valley electrons. And this, of course, has to be done through the presence of phonons. We have to have some momentum transfer in order for this process to take place. But it's the dominant relaxation. If we compare the photoluminescence spectrum for the bare germanium nanowires to the Coreshell nanowires, we can see some very interesting differences. Well, first of all, this is really the first evidence of near-infrared photoluminescence in germanium wires. So this is an important observation. Just that we're seeing a peak here at all is significant, because nobody's ever seen this before for germanium wires. And we do see, Yoko sees a peak consistent with the direct gap transition. It's slightly red shifted relative to this peak here for bulk germanium, and that's consistent with the heating of the nanowires that occurs during this experiment. Nanowires can become heated more easily than a bulk sample, because it's more difficult to extract that heat from a very small cross-section wire than it is from a bulk solid. We also see a strong peak, very strong peak for the Coreshell nanowires. It's more than an order of magnitude more intense, and it's consistent with the indirect transition. It's also redshifted a little bit with respect to the bulk value, similar to the case for the bare germanium nanowires. But we can see a major difference here, so that we're seeing a strong indirect gap transition from the Coreshell wires and a direct gap transition from the bare germanium. So what's going on? In the case of the bare germanium nanowires, these wires were taken out of the growth environment, they were transferred through air, they were put in a photoluminescent system. We know they're going to form a native oxide, and there are many reports of germanium oxide being very defective, having a lot of traps in it. These are slow traps, but in addition having quite a defective interface with the germanium crystal. So we expect to have fast surface states or interface states between the germanium and the germanium oxide, and slower trap states in the germanium oxide itself. If we have enough of these, it's possible for the surface and interface states to quench the indirect gap photoluminescence. So this indirect gap luminescence has to occur, it has to be mediated by phonons, so the rate of this is actually quite slow. We have to wait for the phonon to be available to transfer the momentum from these L-valley electrons toward the valence band. So this process is known to occur with a very long time constant. If we have enough surface states, the non-radiative recombination can dominate over this slow process. However, some of these electrons are in the gamma valley for this germanium crystal. So these electrons can undergo a much more efficient and faster recombination that doesn't require phonons. And so what these results suggest is that the surface state or interface state density is high enough to quench this photoluminescence, but not so high as to quench the direct gap photoluminescence. So Yoko is able to observe a direct gap peak for the bare germanium nanowires. Now if we insert a silicon germanium shell, we still have defective surface oxide and interface between the oxide and the semiconductor, but we've displaced this away from the germanium. It's now separate from the germanium and separated by this silicon germanium shell. So when we're probing the electronic behavior of the germanium core, the influence of these defects may be much less. And so in this case, what we see is that both the direct gap and indirect gap radiative recombination processes can take place, but this is much stronger. There are a lot more electrons in the L valley than there are in the gamma valley, so this will dominate. And we'll see something very much like bulk germanium photoluminescence because of the presence of the silicon germanium shell shielding the core from these defects. The further piece of evidence that Yoko found to support this picture is shown here, that we know from bulk germanium that if we increase the intensity of the excitation in the photoluminescence, we actually prefer the direct gap photoluminescence. So this peak goes up relative to the indirect transition when we have high intensity illumination and excitation of carriers into the conduction band. And the same kind of thing happens here in these nanowire experiments. So our Coreshell nanowire peak now is shifted, and it's become predominantly a direct gap feature, just as we see in the bulk case, bulk germanium case at higher excitation intensity. So these results really do suggest that by forming this shell structure around the core, we capture the bulk electronic behavior of germanium in a very high aspect ratio, high surface area nanowire array. So it's a very exciting result. So concluding remarks, basically we've shown that highly strained, dislocation-free Coreshell nanowires can be grown in the silicon germanium system without any dopants or without any intentional composition changes. We have various methods to do this, but they all involve the inhibition of surface roughening of the shell during growth. If we grow these structures, we found that they still can relax their strain during post-deposition annealing, and interdiffusion of silicon and germanium seems to be an important mechanism for this, particularly at higher temperatures like 700 centigrade. Finally, the photoluminescence data that Yoko collected has shown that the bare germanium nanowires exhibit a direct gap PL feature, direct gap transition, and we believe that that happens because surface defects are sufficiently numerous to quench the indirect gap photoluminescence, but not the direct gap photoluminescence in this material. But if we have a shell present, we can actually capture the photoluminescence behavior of bulk germanium, even in this nanoscopic wire array, by moving the defects away from the germanium. So I'd like to end by acknowledging the sponsors for various parts of this work, and also thank you for your attention.